Hello everyone, my name is Diana Valle, majoring in electrical engineering, and today I will present my proposal on fiber optic sensing for wind turbine blades. Our agenda today includes abstract, introduction and background, project objectives, methodology, design specifications, system architecture, project description, project plan, project budget, conclusion, and references. An accurate, cost-effective stress sensor system is being proposed in which the health of wind turbine blades will be monitored. This proposal examines the integrity of a blade during stressful environmental factors. The system will monitor temperature, excessive strain, and possible damages experienced by the blade. Fiber optic sensing provides a cost-effective solution to monitor the health of wind turbine blades without physical contact, much use of bandwidth, minimal size and weight, and freedom from EMI-induced noises. As the world steps away from fossil fuels, a need for alternative, reliable green energy has emerged. One of those markets is the wind energy market. Optical sensing can provide an accurate and noise-free strain measurements on a wind turbine blade without much added weight to the blade. In the last 25 years, fiber optics has seen an immense growth and development throughout its applications. Fiber optics are very versatile, and its sensor applications can be used instead of traditional sensors in the fields of acoustic, vibration, magnetic measurements and electricity, acceleration, rotation, high temperatures, pressure, strain, humidity, and many other applications. There are two types of fiber optic sensing, extrinsic and intrinsic. When it comes to extrinsic sensing, they are less expensive and easier to use. They are usually used to measure temperature and liquid levels. They can be placed in hard to reach places, and they are not as complex. For intrinsic sensing, they work with direct modulation of light into the optical fiber head. Some of their applications include strain, acoustic pressure, and vibration. They are more expensive, however, and more complex to use. This is a figure showing how an intrinsic fiber optic sensor works. Light goes in through the head, and the detector reaches it at the end. Or project objectives. Design a fiber optic pressure sensor. Perform analytic tests, design schematics to model the system, and execute a sensor response analysis between current sensor systems. Methodology. An intrinsic single-mode fiber optic module was chosen due to its ideal applications. Intrinsic fiber sensing is the better option due to its ability to test for strain, acceleration, and rotation. These are essential applications for our project. This is the design that our team came up with. The single mode optical head, where the pressure will be sensed, how it's going to be put together using epoxy, and the output. We have a system architecture which I don't think you can kind of see, but I will explain. Our control system connected to the fiber optic head will validate process that will check for stress on the blade. It will have boundary checks that will let the system decide whether the blades are healthy or if the blades have been damaged. The system will also have a trigger warning for possible damages. Now for our testing. Testing the proposed sensor system on a working wind turbine blade. We will test for accuracy and stability of the system. A fatigue test will also be implemented to check changes in accuracy and overall health of the system when pushed to its limits. Temperature sensors will also be applied in order to monitor the system's temperature. Our project timeline, it involves 3 months. We will start on March 1st and we should be done by June 29th. Most of the time will be spent in heat testing, strain testing, and any change that should be implemented to make the sensor more accurate. Our project budget includes the purchase of an E200, a temperature sensor, a strain sensor, studs, screws, and epoxy. The E2000 is the fiber optic connector, roughly around $26.99. The temperature sensor, 85 cents. The strain sensor is $13.62. We will need some studs, screws, and epoxy to put the system together and place it into the blade. Conclusion. The proposed system will be an innovation in today's wind energy market. The proposed fiber optic system is innovative, cost-effective, complex sensing system that could exceed the standards set by other sensors in the market today. So far, the proposed system has shown a lot of potential. Each sensor has the capability of providing sensor over distance up to 1 meter. Each turbine blade can be up to from 36 to 100 meters, so having each sensor cover around 1 meter wouldn't fatigue the blade itself. Overall, we feel confident that the proposed project, once installed, will be able to perform well. It will test for stress on each blade and its overall health. The system will have a validation system to check for the danger of failing blades. The system will also validate each answer within neighboring sensor systems to provide a more accurate answer. Here are F references, and thank you for coming.